Good morning. We have studied till now all these different types of cycles which are used for designing industrial gas turbines. So the basic gas turbine cycle, which is known as Brayton cycle, and then different combinations of additional devices such as intercooler, reheating, and regeneration. Okay, and we have seen what are the advantages and disadvantages of that. So all these cycles we have studied till now, assuming that like with lot of assumptions, such as we had considered air for the gas. Okay, so it was ideal gas with air, with constant Cp and Cv values, and all the processes were ideal. There were no frictional losses. A lot of assumptions have been taken. So, but in real life, there are a lot of differences which needs to be accounted for, because the calculation of this work output and efficiency leads to very significantly different values when we consider these differences. Okay, so say instead of 65%, maybe we will get efficiency of only 35%, because if we consider all these changes, there are different losses that will lead to much lower work output, much larger compressor work input, then pressure losses in the combustion chamber. So ultimately, we will get some efficiency which is much lower than the theoretical efficiency that we had obtained for an ideal cycle. Okay. So that's why it is very important for us to study these differences of ideal cycles and real cycles and know how to take them into consideration so that we can calculate the parameters for a real cycle. Okay. And that is what we are going to do in the subsequent few classes. My screen is still visible, right? The screen is also visible, right?
Yes.
Okay. So what are the differences between ideal cycles and real cycles? First, let me just quickly outline them, then we will go through each of them step by step to see how to take them into consideration. Okay. So one is that the fluid velocities are very high, okay, at different locations, okay, depending on uh, the engine, okay. For jet engines, obviously at the inlet and outlet also they are very high. But in between, for industrial gas turbines also, in between in the compressors and turbines, when the fluid passes over the blades, velocities are quite high. Okay. So we cannot neglect the change in kinetic energy. Okay. Change in kinetic energy needs to be considered in the calculations. Okay. So this is the first point. The second point is that till now we had considered that the compression and the expansion process, compression in the compressor and the expansion in the turbine, are reversible processes. Okay, isentropic processes, reversible adiabatic processes. But in real life, they are not isentropic; they are irreversible. Okay, there is an increase in entropy of the fluid during both the processes. So again, that also needs to be considered. We will see how to consider them. I'm just outlining the differences here. Then the third important point is, so this second point is very important because this leads to the most change in the efficiency, okay, from ideal to a real cycle. This change in the losses or the losses in the compressor and the turbine leads to the highest amount of difference between an ideal and real cycle. So this is a very important point, second point. And there are other points which are still important but does not impact the parameters like efficiency to that level, but still important, such as fluid friction, which results in pressure losses. So frictional losses in the compressor and the turbine, we are already accounting for in the second point. Okay, but there are frictional losses in other places also. So there are frictional losses in the combustion chamber. So we are assuming that the combustion chamber process is like a constant pressure heat addition. Okay, but actually what will happen, because of turbulence in the combustion chamber, there will be around 3 to 4% pressure loss that is happening. Okay, so that pressure loss, how will it affect the cycle? It will lead to less pressure difference in the turbine. There will be less scope for expansion in the turbine, leading to less work output. Okay. So that also needs to be taken into account. Just a second. I'm taking certain medications, painkillers, which are causing me, which are like sedatives, causing me a lot of drowsiness. Anyway, let us try to continue. Taking the class itself is has become challenging. So the fourth point is that complete heat exchange is not possible in a regenerator. Heat exchanger means the regenerator. So we have already seen that. Okay. So typically the regenerator effectiveness is around 90%. You can increase the effectiveness of a regenerator by increasing the surface area for heat exchange, but that will lead to more pressure losses. So if there is more pressure losses, again, that will lead to less work output from the turbine. Okay. And the system will also become bulky. So it is not possible to it is not possible to design a regenerator which has very high uh, heat exchange effectiveness. Okay. Same thing is still also valid for the intercooler, but mostly I am saying from the point of view of the regenerator. Then another very important point is that both the temperature as well as the chemical composition of the gases change, right? So if the temperature is lower in the compressor, temperature is very high in the turbine. So the CP value that we take should not be constant or is not constant in the compressor and in the turbine. Okay, because CP is a function of temperature. And similarly, gamma is also not constant. Gamma and CP are means gamma will also get affected. Okay, and the other point is that the CP and gamma they are functions of the chemical composition, so they have a certain value for air. Okay, but so it is fine for the compressor region, but after the combustion process, the subsequent downstream part means in the turbines, all the turbine stages, the composition is different. Now we have carbon dioxide, water vapor, some amount of oxygen and nitrogen. Okay. So that mixture should have a different CP and gamma value. So somehow that also needs to be accounted for. So we may not be able to take that into account extremely accurately in this course. We will have to take certain assumption. But in real life calculations, when you do a calculation or you are designing an engine, a gas turbine in the industry, then you will have to take take this into consideration up to minute details also. Okay. Small changes also. You have to write a computer program and calculate this effect of small changes. Then bearing and windage friction losses in compressors and turbines. So they will lead to small losses. Bearing losses are bearing friction in the bearing. Okay. So you have shaft and on the shaft so basically the shaft is mounted on the casing. The shaft is rotating, its casing obviously is fixed. So there needs to be bearing in between. So there will be small friction losses, less than 1%. Windage losses are also similar. Windage losses are also frictional losses, where the moving parts basically uh, gets some resistance while moving through the air, okay, or the gases, because the moving parts are moving at a fast rate. They get some resistance while moving through the gases which are present in the narrow gaps in the between the casing and the blade. So that will lead to some small losses. Okay. Then one more important point is there, which also we will calculate in our subsequent problems. Okay, which is that the mass flow rate does not remain constant. So initially the mass flow rate is equal to the mass flow rate of the intake air, but after in the combustion chamber we are adding some fuel. The amount of fuel that we are adding is small, around 2%, 2 to 3%, but still it's a change in mass flow rate, and that change in mass flow rate will remain even in the turbines, right? So that 2% increase in mass flow rate will remain in the turbines. So that also needs to be taken into account. Now in jet engines, what happens is that actually the some amount of air is taken out from the combustion chamber or after the compressor for cooling of the turbine blades. So that is another aspect which is known as bleed air. So that leads to a decrease in the mass flow rate in the combustion chamber and in the turbine. But that is a complicated phenomenon that we will not consider in too much depth in our course. Okay. But this is very important, that additional mass flow rate due to fuel. And the final point is that the combustion itself is not 100% efficient. So what do we mean by not 100% efficient? So the fuel has a certain amount of calorific value. It has a certain chemical composition, and we know a theoretical value of energy that will be released if there is complete combustion that occurs. Okay. It will per kg of fuel, there will be a certain quantity of energy that will be released. But because the combustion is not 100% efficient, so we do not get the exact amount of or the theoretical amount of energy from the fuel. Okay. So we can define an efficiency to find out what is the actual amount of energy which is being released. Now for jet engines and for gas turbines, industrial gas turbines, this combustion efficiency is very high, 98, 99%. Why this is very high? Because we use a air fuel mixture where the percentage of air is very large. Okay, so the fuel has lot of air available for complete combustion. As a result, most of the energy that is contained in the fuel is released. This is unlike IC engines. This is unlike IC engines where lot of unburned fuel is there. So combustion efficiency is quite less than 90% in many cases. Here the combustion efficiency is quite high. Okay. So this is, but still it is around 90 to 99%, but not 100%, and that also needs to be taken into account. I want to take a 5 minutes break because I am feeling dizzy, and after 5 minutes, if I cannot continue, I will stop the class. Let us try to continue and see whether we can continue today. Can you hear me?
Yes, sir.
Okay. So let us start one by one. Okay, these effects. Just keep this open. So the first one was fluid velocities are very high. So we cannot ignore the changes in kinetic energy. Okay. So this is actually not very difficult to take into consideration. What is done is that instead of, so we do not explicitly take the velocities or calculate the velocities, at least for cycle level calculations. What we do is we use total enthalpy, total temperature, and total pressure values instead of the static values. Okay. What are these total enthalpies? Already you know, but let me just define again once. Okay. So all the calculations are done in terms of total or stagnation properties. So automatically these values will have the kinetic energy also inbuilt in them. Okay. So total enthalpy is defined like this. So all these total properties like total enthalpy, total temperature, total pressure, they are written with a subscript O at the like with a subscript O, right? So or 0. So H0 is equal to H plus half V square, where H is static enthalpy, which is the normal enthalpy that you know, static enthalpy, and half V square is the kinetic energy, where V is the velocity. Okay. So we can write the total enthalpy as H0 is equal to H plus half V square. Similarly, from the same expression of enthalpy, we can find the total temperature or stagnation temperature. This is static temperature. Okay, this one is static temperature. I have wrongly written stagnation temperature. So stagnation temperature T0 is equal to static temperature T plus half V square by Cp. Okay, so from this expression, if you divide by Cp, you get this expression T0 is equal to T plus V square by 2Cp. So this T is known as static temperature. This is the normal temperature that we measure. Okay. And V square by 2Cp is known as dynamic temperature. So this is the additional component due to kinetic energy of the fluid. So if you use these parameters, and if I try to write the first law of thermodynamics, ignoring changes in potential energy, okay, changes in potential energy are still very less because there are not significant differences in say the change in the height of the fluid. Okay. So ignoring potential energy, we can write the first law for a steady state steady flow process. Like all the processes here are steady state steady flow process in a turbine. Okay. So if the values at the inlet are 1 and the values at the outlet are 2, we can write that H1, which is the enthalpy at the inlet, plus half V1 square, kinetic energy at the inlet, plus Q, which is the heat addition during the process, is equal to H2, enthalpy at the outlet, plus half V2 square, kinetic energy at the outlet, plus W, okay, which is the work output. So H1 plus half V1 square is nothing but H01, okay, which is the total enthalpy at the inlet. And H2 plus half V2 square is nothing but H02, which is the total enthalpy at the outlet. So H01 plus Q is equal to H02 plus W. Okay. So if we do all the calculations in terms of this H01, H02 values, we do not need to separately consider the velocities. Okay. Automatically, they will be part of the enthalpy. This changes in kinetic energy will be part of the enthalpy. So you can just calculate based on the total enthalpy values. So for turbines, we know that there is no heat addition. So this Q is 0. So for the turbine, the work output can be written as H01, W is equal to H01 minus H02. Okay. So this also includes the changes in kinetic energy. Similarly, for the compressor, we can write similar expression. Okay. For the combustion chamber, where the work output is 0, but heat addition is present, W is equal to 0 and Q is equal to H02 minus H01. Again, that also considers the changes in kinetic energy. So the summary is here is that we should use stagnation properties or total properties instead of static properties for doing all the cycle analysis. Okay. One positive side benefit is that positive benefit is that it is easier to measure stagnation properties for high speed flows. Okay. So for example, it is easier to measure the stagnation temperature or pressure for a high speed flow, because when you try to measure these properties, the fluid comes to rest and you are more more accurately measuring the stagnation properties. Stagnation properties, you know, right? So if I uh, bring a fluid to from high velocity to rest, uh, reversible adiabatically, so the values that you obtain are the stagnation properties. So temperatures we know how to calculate. In case you know what is the static temperature and the velocity, we know how to calculate the stagnation temperature. Enthalpy we know how to calculate. The other property which we always encounter is the pressure. So pressure also can be calculated by using the isentropic relation for ideal gas, assuming that this is an ideal gas. So P0, which is the stagnation pressure by P, static pressure, is equal to T0 by T to the power gamma by gamma minus 1. Okay. So as if the flow is reversible adiabatically brought to zero. Okay, this is brought. T is missing here. Brought to zero velocity. This is how we have to take the changes in kinetic energy. So from now onward, for all the problems, we will be writing the same cycles, but in terms of 0, 1, 0, 2, 0, 3, 0, 4, instead of 1, 2, 3, 4. Okay. And doing the calculation in terms of 0, 1, 0, 2, 0, 3, 0, 4. Graphically, what is the difference between 0, 1 and 1 or 0, 2 and 2? So if P1 is the static pressure at the inlet, like the atmospheric pressure. So we have a gas turbine and the atmospheric pressure at the inlet is P1. Okay. And the intake velocity is V1. So typically for industrial gas turbine, intake velocity is very small. So we can ignore that. But for jet engines, we cannot ignore that. That will be quite high. Okay. So then the static temperature, so the stagnation temperature T01 will be higher than T1 by the value V1 square by 2Cp, right? So T01 will be T1 plus half V1 square by 2Cp. The T1 and V1 are the inlet temperature and velocity. So obviously it is at the same entropy line, so isentropic line. So the point 0.01 will be higher than the 0.1 in the TS diagram by the value V1 square by 2Cp. And the constant pressure line through the 0.1 is the stagnation pressure, right? So P01 by P1 will be equal to T01 by T1 to the power gamma by gamma minus 1, where we can easily calculate what is T01 by T1. T01 by T1. T01 is T1 plus P1 square by 2Cp. Okay. Similarly, at the outlet, okay, of the compressor, if the static pressure is P2 and the velocity is V2, the stagnation pressure is, so first we can find the stagnation temperature T02, which is equal to T2 plus V2 square by 2Cp, and then we can find the stagnation pressure P02 by P2, which is equal to T02 by T2 to the power gamma by gamma minus 1. Okay. So like this, we can easily calculate the relation between static and stagnation properties. Any questions? No questions. So the second and the most important difference between an ideal and a real cycle is that in a real cycle, the compression process and the expansion in the turbine are irreversible. Okay. and that leads to large amount of losses, and that needs to be accounted for to accurately calculate the work output and the efficiency. Okay. So why are these losses present? Because of frictional losses. Frictional losses means in this case fluid friction, viscous losses. Okay, processes are irreversible. So we have seen how the ideal cycle looks like. For a simple Brayton cycle, the ideal cycle in a TS diagram looks like this. We go from 0,1 to 0,2s. Okay, so which is the isentropic compression. From 0,2s to 0,3 is the constant pressure heat addition. From 0,3 to 0,4s is the isentropic expansion in the turbine. And we close the cycle from 0,4s to 0,1 by using a constant pressure heat rejection. But in real life, what will happen? Entropy always increases, right? Because of irreversibility. So instead of this 0.02s, the compressor outlet is somewhere on the right hand side of this 0,2s line because the entropy has increased. Okay. The pressure still remains same. Okay. Pressure still remains because by design, you are designing a compressor for a certain pressure ratio. So if I am designing the compressor for pressure ratio of 20, so the outlet pressure will be 20 times the inlet pressure. Okay. So what will be the outlet point? So it will be somewhere on the constant pressure line, but on the right hand side of the ideal point. Okay. Ideally, the outlet would have been at 0,2s, but in real life now, the outlet is at 0,2. Immediately you can see what is the difference because of this. The compressor inlet work, the work that was required for running the compressor was Cp into T02s minus T01. And now the compressor work is Cp into T02 minus T01, right? So we can easily see that now this is the delta T. Previously this was the delta T. So we can see that the work input has significantly increased. Okay. Cp T02 minus T01 is much higher, and it will become more and more higher as we have more and more inefficiency. So a compressor which is less inefficiency, less irreversibility, like say it goes like this. So in that case, the extent of extra work due to this irreversibility is less. But a compressor which goes like this, you see that lot of extra work is needed. Similarly, for the turbine, what is happening? So ideally, the turbine exhaust should have been at 0,4s. But because of irreversibility, now the actual exhaust occurs at 0,4. Okay, which is at higher entropy. Entropy is always increasing, right? So as a result, what we are getting less work output. So ideally, we would have gotten something like the size. So ideally, we would have gotten something like this much work output, but now we are getting this much. So this is the reduction in work output that is occurring. Okay. So ideally, we would have got Cp T03 minus T04s. Now we are getting Cp T03 minus T04. Okay. And again, the more the irreversibility, more will be the decrease in the work. So if I have a process like this, you will get even less. Okay, even less work. So this is what is the difference in both the cases. Okay, and the isentropic points or the ideal points are denoted by these S values. So, okay, it is not arbitrary. You cannot just write that this is 0 to A and this is 0 to, because that is not the correct convention. So you have to write this as 0 to S only. Okay, otherwise it's not correct. Similarly, this is 0 for S. This is the standard convention for writing the isentropic points. You cannot write that this is 1, this is 2, okay, this type of things. This is the standard convention followed in industry and academia. So this is how the real cycle becomes then in that case. Okay, after the change, it goes from 01 to 02, from 02 to 03, 03 to 04, and from 04 to 01. Okay, this is the real cycle, real Brayton cycle. So if you want to, this we have written, this we have drawn in terms of the total properties. But if you want to understand how the static and stagnation properties both change, okay, which we, at this point we just can calculate based on total properties. But if you want to know, so this is how it will look like. Okay. So this is the static property at the inlet. So static pressure and static temperature. This is the static temperature and this is the static pressure. P1, right? And this is the stagnation pressure. P01. And this is the stagnation temperature. So T01 by T1 is T01 is equal to T1 plus V1 square by 2Cp. So we know the inlet condition. Now ideally at the outlet, we should have had some static condition 2s and stagnation condition 0 2s. Okay. But what is happening because of change in entropy, increase in entropy, we are obtaining a static condition 2. At that point, there will be some velocity. Okay, at that point, there will be some velocity. And the stagnation condition will be 0 2. Okay. So if we want to keep at the same pressure line, so if you want to design with the same pressure line, it will be. So it can also happen that I have lesser velocity at the outlet as compared to the ideal situation. So this to this point. So this may become my stagnation point. Okay, it is up to us to decide. So again, 2 and 02 are related. T02 by T2 is equal to, or P02 by P2 is equal to T02 by T2 to the power gamma by gamma minus 1. And T02 is equal to T2 plus V2 square by 2Cp. Similarly, T02S is equal to T2S plus V2S square by 2Cp. Okay. So to summarize, the work input for the compressor is increased, work output from the turbine is decreased. Okay. So we are getting heat from both sides. Work input also increases for the compressor, work output also decreases from the turbine. So efficiency gets quite a bit of efficiency decreases by quite a bit because of this. Can you tell me typically whether turbines have higher isentropic efficiencies or compressors, and what is the reason for that? Because you must have studied about turbines and compressors, or at least from thermodynamics point of view, you can, or fluid mechanics, you can relate. And we have discussed this towards the beginning of the course.
Sir, turbine has higher efficiency than compressor.
Correct. Why? Why is the reason?
Sir, because it operates at higher temperatures, so.
No, that is not the correct reason. Efficiency is higher, that is correct. But what is the logic? You cannot just memorize the answer, you have to think logically. Efficiency is higher, isentropic efficiency, because of what does it mean? Frictional losses are less, right? That's why efficiency is higher. Fluid frictional losses are less. So why are fluid frictional losses less in a turbine as compared to compressor? What is the fundamental difference in the flow pattern in a turbine and compressor? We have discussed this.
Sir, in compressor, air goes against adverse pressure gradient. And in turbine, it flows against a favorable pressure gradient.
Correct. That is the point. So in compressors, the flow is, so the pressure is increasing in the compressor from the, say, inlet to the outlet, and your flow has to also go in the same direction from the inlet to the outlet. So flow has to travel against a increasing pressure. Okay, so its flow has to travel against adverse pressure gradient, which leads to more chances of separation. So it is much more difficult to means in that sense for the flow to occur. So typically compressors have lower efficiency. Turbines, on the other hand, the flow travels from high pressure to low pressure region. Okay, so from higher pressure to lower pressure. So in favorable conditions. So as a result, less chances of irreversibility or flow separation and higher efficiencies. So this efficiency, this difference between the ideal and real cases are taken into consideration by defining isentropic efficiencies. This you must have studied in your thermodynamics course, but again we will just revisit them because it's very important for our course. So we define an isentropic efficiency. We define an isentropic efficiency for the compressor as beta C is equal to H02S minus H01, which is the ideal work input, divided by the actual work input, H02 minus H01. Okay. If we assume that Cp is constant, we can take out Cp, and Cp gets cancelled. So we can write this as T02S minus T01 by T02 minus T01. Obviously, this is less than 1, the efficiency, the way it is defined, because T02 minus T01 will be higher than T02S minus T01. Typical values are around 90%, 85% to 90%. Turbine efficiency is also defined in somewhat similar way. So the actual work output by the ideal work output. Okay. So H03 minus H04 by H03 minus H04S. H03 minus H04 by H03 minus H04S, which can be written as T03 minus T04 by T03 minus T04S. Okay. So again, actual work output is less divided by the ideal work output, which is more. So if obviously efficiency is defined in that way, so that the efficiency is less than 1. Okay. So compressor, so based on these efficiencies are property of the turbine and the compressor. Turbine efficiency may be around 90%, 91, 92%, right? So if it is known, the efficiencies are known, we can calculate the actual changes in the actual work input and actual work input to the compressor and actual work output from the turbine based on the efficiency and pressure changes. Pressure change, remember, is an input parameter. Okay, we have already discussed the two input parameters are pressure ratio and the temperature ratio. So compressor pressure ratio is an input parameter, design parameter, which is decided by the designer themselves while designing the cycle. Okay, so it is already fixed before designing the cycle, okay, based on other considerations. So once this is fixed, we want to calculate what is the work input in the compressor and the work output from the turbine. In the case of actual compressor and turbine with losses, we need the efficiency values to actually calculate the work input and work output from the compressor and turbine. So we can directly calculate in your problems, but if you want to do them in using like analytically, it looks like this. So for the compressor, T02S by T01. Remember that let me just T02S minus T01 by T01 is it's an isentropic process, right? So is equal to P02 by P01. Okay, P02 by P01. So P02 by P01 is the compression pressure ratio. Let us call this as RC. Okay. So RC to the power gamma minus 1 by gamma. So now we know that efficiency of the compressor is T02S minus T01 by T02 minus T01. Okay. Increase the size. So this we can write as, if we take T01 as common, it will become T02S by T01 minus 1. So T02S by T01 we have already seen is RC to the power gamma minus 1 by gamma. So we can write in this form, eta C is equal to T01 RC to the power gamma minus 1 by gamma minus 1 by T02 minus T01. Or the work input to the compressor can be written as Cp into T02 minus T01, which is equal to Cp T01, means from this above expression, this is equal to Cp T01 into Rc to the power gamma minus 1 by gamma minus 1 by eta C. So this is in terms of known parameters. So work input of the compressor we can find out in terms of known parameters. T01 is the inlet stagnation temperature, which is known. Right, static temperature is known, velocity should be known for the calculation. So, or we will assume the stagnation temperature is known. Typically, the stagnation temperature is equal to the atmospheric temperature. Okay. Because in the atmosphere, we are assuming that there is no velocity for industrial gas turbine. So, stagnation temperature is equal to the static temperature. RC is a known parameter, compressor pressure ratio. Eta C is a, based on manufacturing, it is also known, means it is the isentropic efficiency of the compressor. So work input to the compressor can be calculated like this. Obviously, you can see that if eta C decreases, means if the efficiency decreases, the work input increases for the compressor. Exactly similar analysis you can do for the turbine. Eta T is equal to T03 minus T04 by T03 minus T04S. So which we can write as T03 minus T04 by T03 if you take common, 1 minus T04S by T03. What is T04S by T03? It is 1 by RT to the power gamma minus 1 by gamma, where RT is the pressure ratio across the turbine. So work output from the turbine is Cp T03 minus T04. Again, from the above expression, you can write this as Cp into eta T T03 1 minus 1 by RT to the power gamma minus 1 by gamma. If you assume that the pressure ratio across the compressor and turbine are same, then we can just replace this by R and R. Okay. So instead of RC, we can write R. Instead of RT, we can write R. Okay. In real life, the pressure ratios are not same. Why it is not same? At this point, we'll assume it to be same. But later we'll see that the pressure ratio across the turbine is different from the pressure ratio across the compressor. Why? What may be the reason? Primary reason for this?
Pressure loss
So in case of compressors, so lower pressure gradient across the compressor will be present.
Lower pressure gradient across the? No, I could not understand your point.
So at each compressor stage, lower pressure gradient has to be present.
So what?
So that
I can have large number of stages. I will have larger number of stages. Yes.
Pressure loss in combustion chamber.
Correct. So there is pressure loss. So compressor we are designing with a certain compression ratio in mind, right? So say compression ratio is 30. So if one stage cannot handle much like pressure ratio, we will have more number of stages. That is not a difficult thing. So, but say if you have 30 as the compression ratio, overall compression ratio, there will be some pressure loss that is happening in the combustion chamber, say 3 to 4%. So if the inlet pressure at the compressor was 1 atmosphere and outlet pressure is 30 atmosphere, after 4% pressure loss, instead of 30, how much loss is there? So 4% loss is there. So you will get 28.8 instead of 30. 28.8 atmospheric pressure at the inlet of the turbine. Outlet of the turbine still has to be atmospheric pressure. So the pressure ratio now has become 28.8 instead of 30 across the turbine. So pressure ratio will decrease across the turbine. So as a result, that also affects the work output, which we'll study later. But that's why we can have different pressure ratios across the compressor and turbine. At this point, if we, for simplification, if we assume that RC is equal to RT, we can simplify further, as we will see. Okay. So one point is that, so anyway, this is how you can calculate turbine work and compressor work in terms of known parameters. T03 is known. How is T03 known? This is the maximum temperature, which is the temperature limit again set by the designer based on the turbine material properties. And eta T is known, and RT is also known. Okay, so if eta T is decreased, again you can see that work output from the turbine gets decreased. Okay, so we want this to be as high as possible. One point is that sometimes in calculations, it is considered that the exhaust gas of the so the kinetic energy of the exhaust gas is lost, and that is also taken into consideration. So instead of stagnation properties at the exhaust point, okay, at the exhaust part, we just consider the static properties, because that extra kinetic energy that was present there, that is not being, we are not being able to use that kinetic energy. Okay, so in that case, sometimes eta T is defined as T03 minus T03 minus T4 by T03 minus T4s. Instead of T04 and T04s, we are writing T4 and T4s instead in terms of static properties. Okay, because we cannot use the kinetic energy at the exit part, at the exhaust part. We are assuming that the energy that is present there, or the change or the work output that is happening, is the difference between the stagnation property at the inlet and static property at the outlet. In that case, again, you can write a similar expression. So eta T is equal to T03 minus T04 by T03 if you take common, 1 minus P03 by P4 to the power gamma minus 1 by gamma. P4 and P04 can be easily correlated based on T4 and T04, and from there you can find out this ratio also, and WT can be calculated. Once you practice some problems, it will be clear. So another important point is that due to compressor inefficiency, okay, although more work needs to be added, okay, so you can see that because of compressor inefficiency, we have seen that more work is needed in the compressor. This means that the entry temperature to the combustion chamber is higher. Okay, as a result, for the same cycle, we need less heat addition in the combustion chamber. So somewhat it is mitigated. The inefficiency, the losses by the inefficiency, is somewhat mitigated because of less amount of heat required in the combustion chamber. Okay, so although the entry temperature, so input work in the compressor is quite high, the amount of heat addition that is required in the combustion chamber is less, because we are the gases are entering the combustion chamber at a higher temperature. So that is also one important consideration. Okay, so there may be a situation when there is no work output at all. Okay, in ideal cycles, we will have work output always. That work output from the turbine will be greater than the work input to the compressor. Why? Because these constant pressure lines are diverging. The distance between the constant pressure lines for the turbine will always be greater than the constant pressure lines between for the compressor. But for real cycle, now because T02 minus T01 is higher than that of ideal cycle, and the T03 minus T04 is lower, there can be a situation where T02 minus T01 is equal to T03 minus T04. As a result, the turbine work output is just sufficient to run the compressor. We do not get any actual work output. This is done when WC is equal to WT, and this happens when if you equate these two works, okay, so and assume that RC is equal to RT, So Cp T01 by eta C R to the power gamma minus 1 by gamma minus 1 is equal to Cp T03 eta T 1 minus 1 by R to the power gamma minus 1 by gamma. If you do some cancellation, Cp gets cancelled. We can write T03 by T01 after doing some calculations. This T03 by T01 comes out as R to the power gamma minus 1 by gamma by eta C eta T. Okay. So if the temperature ratio is related to the pressure ratio and the efficiency in this way, okay, so then we will not get any work output. Okay, so there is a minimum value. This is a minimum value of temperature that is required. If minimum value of temperature ratio, if the temperature ratio goes below this value, there is no work output. Okay, so if you have a larger value of R, you need a higher temperature ratio to obtain some work at least. Okay. Similarly, you have a lower value of efficiency. Obviously, you need a higher value of temperature ratio to get some work output, because lower efficiency is not beneficial. Similarly, lower turbine efficiency is not beneficial. So you need larger amount of temperature ratio to get some work output. Okay. The minimum temperature range increases if you have larger pressure ratio. Larger pressure ratio means more losses in the compressor and more losses in the turbine. And lower efficiency means also more losses in the compressor and more losses in the turbine. That's why you need larger temperature changes to get some useful work output. Okay. So this is also an important relation. So we'll stop here and we'll continue this discussion in the next class.